Unit 4 is the study of special functions. We began by examining rational functions in section 4.1. Remember, rational functions can have vertical, horizontal, or oblique asymptotes. Another pair of functions that can contain asymptotes are exponential and logarithmic functions. The key to understanding the relationship between exponential and logarithmic functions is to realize that they are a pair of inverse functions. Let's begin looking at the first half of this inverse pair of functions, exponential functions. For real number a greater than 0 and a not equal to 1, the function f of x equals a to the x defines an exponential function with, now here's the key, constant base a. We've studied a lot of exponents this semester, but we never called anything an exponential function. So we need to answer the question, what's the difference between the exponential function f of x equals 2 to the x and the power functions that we've seen, like g of x equals x squared? Hopefully you can immediately spot the difference. The exponential function 2 to the x has a variable in the exponent and a constant base. Whereas our polynomial functions, or in particular this power function, has exactly the opposite case. In the exponent, we have a constant, and in the base, we have a variable. So we're careful to call this a power function, not an exponential function, because to be classified as an exponential function, it must have a constant base. And note that base has to be positive and it cannot be equal to 1. So let's take a look at a couple of varieties of exponential graphs. So you're going to have two possible exponential graphs. The first one is an increasing exponential function, and this occurs when the base is greater than 1. And the second possibility is a decreasing exponential function, and this occurs when the base is a fraction between 0 and 1. One's increasing and one is decreasing, but both functions have the same properties. Now, anytime you want to begin graphing an unfamiliar function, one way to do that is by plotting points. So what we could do for our exponential function, a to the x, is choose some x values and calculate the corresponding y values. So we could choose small, easy to work with x values like -1, 0, and 1, and we could plug those values in for x and then calculate the output. And what we come up with are 3 key points. So notice on our increasing exponential function, we have 3 key points here in the middle. X values are -1, 0, and 1. And on our decreasing exponential function, we have 3 key points with the same x values, -1, 0, and 1. Both of those functions share the same y-intercept. Observe on both graphs, the y-intercept is 0, 1. That's our middle key point there. Now, while the first function on the left is an increasing function, it's actually going to settle down on the left side above this horizontal asymptote. It's never going to touch the x-axis and it's never going to cross it. For our decreasing exponential function, the same thing happens, but it's on the far right side of the graph. The function decreases down to the x-axis, but it never touches it and it never crosses it. For this reason, we have a horizontal asymptote on the x-axis whose equation is y equals 0. Now, the reason for that is because there's no possible value that I could plug in for that exponent x and get either a 0 or a negative value as the output. Now, both of these functions, whether increasing or decreasing, have the same domain. It's always going to be -infinity to infinity. But because all of our y values are above the x-axis, our range would be 0 to infinity. Exponential functions are some of our most important functions for modeling real-life phenomena. For example, we use an increasing exponential function to model cell division, population growth, or investment like compound interest. Decreasing exponential functions can be used to model radioactive decay, medicine level in the bloodstream, or even Newton's law of cooling. So with these two new parent functions in mind, let's see if we can graph a couple of basic exponential functions. So example 1, complete the table and use the information to graph the exponential function. Be sure to plot the asymptote on the graph. Remember, every exponential function will also have a horizontal asymptote. And then we'll identify the domain and range. So the first function we want to look at is 2 to the x power. Now, 2 to the x power is a basic exponential function, and we want to generate the 3 key points. The way we do that is by choosing x values -1, 0, and 1. And we're just going to plug these into the function. So if x is -1, and we plug that in for the exponent, the output is 2 to the -1, or 1/2. If x is 0, we'd evaluate 2 to the 0th, which is 1. And if x is 1, we get 2 to the 1st, which is equal to 2. So this gives me an ordered pair, or a set of ordered pairs to plot. The first one would be -1 and 1/2. My second ordered pair is that familiar y-intercept, 0, 1. And then we have ordered pair 1, 2. Now remember, our basic exponential functions have a horizontal asymptote automatically on that x-axis. So I'm going to go ahead and sketch that in and label it before I draw the curve. So the idea is the left side settles down above that horizontal asymptote, and the right side, we say, increases exponentially. So this is the exponential function y equals 2 to the x. Now the interesting thing about this function is it can be used to model basic cell division. Think about learning about mitosis in your biology class. You start out with a single cell that goes through the mitosis process, copies the DNA, and divides into 2 identical daughter cells, right? And then each of those 2 new cells goes through the mitosis process, and they divide into 2 copies of themselves. So if we call that first one iteration 0, we have 1 cell. After 1 iteration, we have 2 cells. After 2 iterations, we have 4 cells. So notice those are the points: 0, 1, 1, 2, 2, 4. So we can count the number of cells that will be in the organism after a certain number of iterations of the mitosis process. Now, as the population grows, the number of cells increases dramatically. So we call that exponential growth. Now, looking at our graph, we can identify the domain as the set of all x values used on the graph from left to right. The domain for every exponential function will be -infinity to infinity. And the range will be from 0 to infinity. Those are my y values from the lowest to the highest. We start just above that horizontal asymptote, so we have a parenthesis at 0. Now, every increasing exponential function is going to have this same basic nature. But as I change the base, if I increase the base, then it's going to increase a little faster. Or if we decrease the base, it's not going to increase quite as fast. But that's the basic nature of an increasing exponential function. Let's look at an example where the base is a fraction. So in this case, we have 1/2 to the x. To get the 3 key points, notice we're using the same 3 x values, -1, 0, and 1. So if we plug -1 in for x and evaluate 1/2 to the -1, that's going to give us 2. 1/2 to the 0th power gives us 1. And 1/2 to the 1st power gives us 1/2. So we've got 3 ordered pairs that we could plot to begin examining this graph. So we have ordered pair -1, 2, the familiar y-intercept 0, 1, and 1, 1/2. And then remember, we have a horizontal asymptote, that lower boundary line on the x-axis called y equals 0. So in this case, when we connect the points, we have a decreasing exponential function. And that is our function, 1/2 to the x. Observe, the domain is still -infinity to infinity, and the range is 0 to infinity. So once again, a base bigger than 1 creates an increasing exponential function, and then a fraction base between 0 and 1 creates a decreasing exponential function. Both graphs have the same domain and range and the same y-intercept, and we generated the 3 key points with the same x values. If you can remember those basic characteristics, then exponential functions are pretty easy to deal with. Let's look at example 2. Now that we have a new parent function, of course we can execute transformations. So we want to use transformations to graph the exponential functions and then state the domain and range. So on our first example, we have f of x equals 1/3 to the x minus 2 minus 3. We want to notice here that our parent function is the basic exponential function y equals 1/3 to the x. So we have a decreasing exponential function. So I'm going to start by graphing the parent function by generating those 3 key points. I'm going to use the 3 x values, -1, 0, and 1. So if we plug -1 in for x, we have 1/3 to the -1 power, which of course gives us 3. 1/3 to the 0th power is 1, and 1/3 to the first power is 1/3. So we've got ordered pair -1 and 3. Ordered pair 0, 1, notice we're getting the same y-intercept every time, and ordered pair 1 and 1/3. And before I connect the dots, I want to construct my lower boundary line here on the x-axis. That's the horizontal asymptote y equals 0. And this is our decreasing exponential function. That is our parent function. So let's go ahead and label that as 1/3 to the x. But remember, our original purpose was to graph this function f of x. F of x has 2 transformations. Now remember, if you subtract a constant from the function outside of the argument of the function, it's a vertical transformation. Because we're subtracting 3 here, we're going to move that parent function down 3 units. In the argument of the function, which now lives up in the exponent position, notice we're subtracting a constant. That's going to be a horizontal transformation to the right. So we're going to move that parent function to the right by 2. So I'm going to take those original 3 green points and move them each right 2 and down 3. So I'm going to start with my leftmost point here. I'm going to move it right 2 and down 3 and make a new point. Look at the intercept 0, 1. We're going to move it right 2 and down 3. And this point, right 2 and down 3. Now think about that asymptote. It's also going to transform. If I slide that asymptote to the right by 2 units, it's not going to change its apparent position. But if we move it down 3 steps, we can see it changes its position and lands at y equals -3. So that's going to be our new lower boundary line. And we can connect our dots. We have a decreasing exponential function. Same nature as the parent function, but new location. So looking at just this newly created blue curve, the transformed function, let's look at the domain and range for that function. The domain has not changed. It's still -∞ to infinity. But remember, the range goes from the lowest y value to the highest value. So looking at the blue curve, remember it levels out above that horizontal asymptote y equals -3. So the lowest y value, but not including, is -3, and the highest y value is infinity. So the domain of an exponential function will always be -∞ to infinity. The range will be dependent on the location of that asymptote. And remember, you can check all of that information with your calculator. Let's look at our next example. We have g of x equals -4 to the x minus 1 plus 2. So let's begin by graphing our parent function, which is just the exponential function 4 to the x. Because the base is bigger than 1, we can anticipate this being an increasing exponential function. So let's generate the 3 key points for our parent function. If x is -1, y would be 4 to the -1 or 1/4. If x is 0, y is 4 to the 0th or 1. And if x is 1, y would be 4. So we have our 3 key points in the form of ordered pairs. Our first one is -1 and 1/4. 0, 1, the familiar y-intercept there, and ordered pair 1, 4. Don't forget, we're going to have a horizontal asymptote on the x-axis, limiting the curvature of our graph. So we have an increasing exponential function. Notice that one's increasing faster than 2 to the x that we did on the previous page. So that is our parent function, but we want to graph the transformed function. Now the first thing that I notice is our function is multiplied by a negative. Let's execute that transformation before we take care of the other two. Recall, if you multiply by a negative, that's going to reflect your graph across the x-axis. Now, because the original horizontal asymptote is on the x-axis, when I reflect it, it's not going to move. But we can take each of these points and reflect them to the other side of the x-axis, and we end up with the mirror image of our function on the other side of the x-axis. So that would be the curve negative 4 to the x. Now, the other two transformations we can knock out on one step. The minus 1 up in the exponent position is going to move this curve right by 1, and the plus 2 outside the function is going to move it up 2. Now, let's talk about the location of the asymptote first. If I move it right 1, it's not going to change its apparent position. But when we move it up 2 spots, we can see it land at the location y equals 2. Then we'll take each of those black points, move them right 1 and up 2. So we're going to go right 1 unit, up 2, right 1, up 2, right 1, up 2. And then create a curve that's the same shape and size as the black curve, but it is just in a new location. And that's our function. Actually, we call that one g of x equal to negative 4 to the x minus 1 plus 2. Now, just examining that final blue curve, the domain, as always, is negative infinity to infinity. The lowest y value used on that blue curve is negative infinity, and the y values increase up to but don't include that horizontal asymptote at 2. So this is the basic exponential function. In the next video, we'll start looking at the inverse exponential function, which we call a logarithm.